So this is the most heavily damaged area. Yeah, this is bad.
When the earthquake hit, even though a magnitude 7 earthquake is not the maximum earthquake that this place could experience, I knew it was large enough to cause a lot of damage.
Here we are at the Presidential Palace.
But it was quickly apparent within a few days that some areas had been affected much more so than others. So now what we're trying to do is to learn what is the relationship between the type of geology and the amount of destruction.
When an earthquake happens, it's a very unfortunate event, but it's something that we need to take the opportunity and learn from. There were some complicated things that happened with this earthquake in terms of understanding the damage patterns. Why were these buildings damaged in this area when they weren't damaged over here and the construction appeared to be very similar? Well, there was something different about the way the ground shook in certain areas of the city during the earthquake.
It's really bad over there.
So an earthquake is caused by a slip in the earth. And that slip creates these seismic waves that travel from deep in the earth out. And as the waves come up under your building site, they're propagating out of the rock and through the soil. That's why we try and characterize the stiffness of the soil, because it really has a profound effect on the level of ground shaking. This is where we tested before, and I just want to do some shallow testing here and see if the results are similar to what we got before, because this was a bit of a strange location. So just walk down there and I'll stop you.
The stiffness of the soil is quantified by something we call a shear wave velocity.
Okay, I'm going to hook up some cables.
And that's simply the speed that shear waves, which are the waves that are generated by the earthquake, it's how fast do those waves travel through the soil.
So Brady is setting up these geophones, and they're going to measure vertical motion, the up and down. And we're going to use the sledgehammer to generate surface waves, so waves that travel along the surface. And as they travel underneath the geophones will vibrate. So we'll be able to see the speed of the waves as they travel from sensor to sensor.
Now, as long as the analyzer works, we'll be good. Okay, go ahead. Okay, again. That's good. We've got 1,500 feet per second, 10 feet deep is what it's looking like right now.
It's pretty good stuff.
Yeah, it is.
It's stiff, it's strong. It's not going to increase the level of shaking significantly. So the shaking level here might have been moderate.
All right, one more. Okay, that's it.
So what we'll do now is check out different roads, make a stop, collect a data point, and a GPS measurement.
Okay, go ahead. Again.
We've observed and we've measured the shear wave velocities around the rest of Port-au-Prince.
Looks good, again.
And the majority of Port-au-Prince actually has stiff, what we would call pretty good soil. The place where it's not as well off is right downtown, within about 1 or 2 kilometers to the coast. And this is where you start to see softer sediments, and that's where a significant amount of damage was.
We've begun to really piece together the puzzle where we can say those really soft soils have a tendency to amplify waves that are coming from the earthquake. So you will have to design your structure to resist higher forces if it's built on soft soil.
I mean, usually it gets stiffer as you go deeper.
And we're trying to help the structural engineers predict the level of ground shaking that the structure needs to be designed for.
be a weathered soil horizon on top, or it could be some.
When I am designing something and I am calculating the structures, elements like the beams for the house, I must know about the seismic effect, and I should include it in the building.
The reconstruction process is starting, so that's why it's important to make smart decisions based on the data that is being acquired and delivered this week, plus general considerations about what we know about how to build from experiences elsewhere in the world.
There are a lot of geologic correlations between Port-au-Prince in the San Francisco Bay Area. First off, they both are in very active fault zones. Both of them have similar soil conditions and fairly hard bedrock material, so the level of ground shaking would be pretty comparable. In the Bay Area, we're probably looking at very similar levels of shaking as what was experienced in downtown Port-au-Prince.
Certainly San Francisco, the Bay Area, has been really at the forefront of seismic design and has a particular concentration of experts, research, and actual buildings that are constructed. So it really is a working test laboratory. In earthquakes, the ground's shaking and the building starts to shake back and forth. And the biggest risk they carry is the separation of the walls from the floors. What we're trying to do is utilize continuous cables to stabilize the massive wall and bring that structure back.
So these extend all the way down into the foundation mat.
That's right. We essentially have hollow ducts that we've been casting into the concrete. And those hollow ducts provide a pathway for cables. Once the cables are inserted, we take those cables and stretch them and compress the concrete walls. And during an earthquake, it rocks back and forth, it forms cracks, and those continuous cables help bring the wall back, close the cracks, and bring the building back to its original position.
The cables are positioned essentially to be centered in the wall. So for each length of wall, there's a cable essentially running right down there.
While these cables are incorporated into the structure in a slightly different way, technologically there's supplies and materials that are available throughout the world. It's a technology that's available to almost all societies basically doing concrete structures.
For a lot of poor countries, it's difficult for them to accommodate seismic design. But then on the other hand, the cost of a disaster is extreme.
We know that the January 12th earthquake was not the large earthquake that may hit Port-au-Prince. So we have two solutions. We can say, well, earthquakes are a tough problem to deal with, and we have other priorities. Or we are proactive about it and say, let's use a reconstruction as an opportunity to build better, as an opportunity to move forward, as an opportunity to develop a seismic risk reduction program, because if we don't do it now, we will never do it.